Hello, and welcome back to the course. So today we're going to look at inverses of holomorphic functions. And we've looked at inverses before, but we're going to prove more today. So this is section 5.6 in the book, and you can get the book in the link in the description. All right, so let's restate. This is basically the theorem that we saw last time, except it's slightly stronger than what we saw last time. So last time we had the inverse function theorem with the extra hypothesis that that f prime to the derivative was continuous. So we already know that it always is, so we can just not put it in the theorem, right? So the idea is that if we have a holomorphic function on some set U, so let me just quickly go through this, right? And we have some point P in U where the derivative is non-zero, then there exists these open sets, so a neighborhood of P, V, and W, which is the image of V under F, and the restriction of F to V is 1 to 1, so it's invertible, and the inverse is actually holomorphic, and then we can actually compute the derivative even, right? So this is the local version. You know what we can say about how we can, if we know something about the derivative, how what does it say about injectivity, right? And so in other words, if f prime is non-zero somewhere, then f is injective near that point, right? But it's not necessarily injective globally, of course, right? So if we have the function z squared, right? So that takes the punctured plane to itself, right? And f prime never vanishes. F prime is, never vanishes on the punctured plane, right? It vanishes at 0, but if we're interested in the punctured plane, then it never vanishes, right? Because the derivative is 2z, and so that's only 0 when z is 0, right? But this function is not 1 to 1. It's actually 2 to 1 globally. Locally, it is always 1 to 1. So if you restrict to a small neighborhood, of course, you get 1 to 1. But there's, if you look at the function globally, there's always 2 points that go to 1 point, right? So there's the 2 square roots, right? Every number except 0 has 2 square roots. All right. So now, basically what we want to do is we want to look at the other direction. So what if we have an injective function? What does it say about the derivative? Right now, we know what the derivative says about injectivity, right? It says you get injectivity locally, right? Because derivative is a local thing. We don't expect anything global. Anyway, so for real functions, just functions of a real variable, let's just say, right? Non-holomorphic, right? Well, injectivity doesn't say much. I mean, even this really simple one, x cubed, as long as x is real, right? So we're taking a function of a real variable, so it takes the real numbers to the real numbers. Well, x cubed is injective, but the inverse is the cube root, and that's not even differentiable at the origin, right? And that's really because f, the derivative at 0 to x cubed, right? The derivative is 2x squared, and that's 0 at the origin, right? So the inverse function theorem, the regular real inverse function theorem, doesn't apply here, right? So the inverse is just not not differentiable even, right? And it's really because the f prime vanishes, even though the function is injective, right? X cubed is injective, so so we can't say anything in the real case. But in the holomorphic case, all holomorphic functions are actually locally sort of like z to the k, right? But here, if we're talking about holomorphic functions, we're talking about complex z's, right? And so near the origin, z to the k, the only time that it's injective is k is 1, right? There's, if you look at z cubed, right, there's always 3 different small numbers, right, that go to any particular other small number, right? Under this map, right? So z cubed is 3 to 1, generically in any small neighborhood of the origin, right? So it's only going to be injective if k is 1, right? So that means, well, if k is 1, if the function really locally behaves, up to a small holomorphic change of variables, if it really behaves like z, right, then it's actually injective, right? Of course, that's just this is just intuition. We have to prove this. All right, so let's prove this fact, right? So that if we have a holomorphic injective function, then the derivative is never 0, right? So, well, let's start with a non-constant f, and let's suppose the derivative is 0 somewhere, right? I mean, it's we're either going to get a contradiction or we're going to show that the function wasn't actually injective, right? It's the contradiction, right? So because it's non-constant, f prime can't be 0 identically, right? So it's injective, it's non-constant, right? So that means that the derivative has isolated zeros, right? So let this closed disk delta R, the closure of that, be such that it fits in U, including the boundary. And let's suppose that f prime only has a 0 at P on this disk. So there's no other zeros of f prime on this disk, right? Now, there is some delta such that on the boundary of this disk, this f of z minus f of p is at least delta, right? Right, we can always, for a small enough disk, that's always true, right? That we can do that, right? Because f also has, f of z minus f of p as a function of z has also isolated zeros, right? So there's always some delta like this, right? Some disk and then some delta, right? All right, so now this function, f of z minus f of p as a function of z, that has a multiplicity of at least 2. Why? Well, because the derivative of this is 0 at p, right? And so it definitely has a 0 at p, right? When z is equal to p, well, that's f of z minus f of p is 0. The derivative in z, right, of this thing is 0 there. Therefore, the multiplicity of that 0 has to be at least 2, right? Now, by the way, notice, so you're thinking, well, aren't we done? Are we gonna get, then always, two things going to the same thing? Well, I mean, we really have to prove that we have two distinct, points going to the same one to prove that, or at least two distinct points going to the same thing, right? So this guy has 0 of multiplicity at least 2, right? But there's it's really the only one, at that point. And then we're going to look at some points nearby, and we have to then prove that those guys don't have multiplicity at least 2, right? That those are all going to be simple zeros, and that's going to give us two distinct points, right? So, all right. So let's do those details, right? So let's suppose that we take a W in this punctured disk of radius delta, this delta, right? Centered at f of p, right? And with, not f of p. We know that the 0 is of multiplicity 2 there, right? So let's take any other W in the, in this disk. And then we look at f of z minus w, right? Now, that by Rouchet, I mean, we've done this argument before, right? That by Rouchet has 2 zeros. It has 2 zeros in here, right? So in this disk, right? So it's definitely, none of these, it's actually 2 zeros in the puncture disk as well, right? The only thing that goes to, that would be when W is f of p, and we know that it's not, right? So it's at least 2 zeros in this function disk. So what we have to prove is that there are 2 distinct zeros, right? There's 2 distinct points that f takes to W, right? So, right, Rouchet only gives you up to multiplicity, right? So if we want distinct, we have to, show that they are actually distinct, right? That they're not the same point with higher multiplicity. But f prime is non-zero on this entire thing, right? That zero, right? These two zeros, right, that I'm getting by Rouchet, are in this set. F prime is not zero in this set, and that's the derivative of this function as well, right? The derivative of that function is f prime, right? Because w is just some constant, right? Therefore, all the zeros, in this disk are simple, and that means that f of z minus w has two distinct zeros in this set. Well, that just means that it's not one-to-one, not even locally one-to-one, right? So once we have that f prime is non-zero, we get that it can't be locally one-to-one. That's precisely what this this statement is. It's, basically we're just showing that it's it's sort of like z to the k, where k is bigger than 1, right? So, all right. Now we can actually, compute the inverse, or we can have a formula for the inverse once we have an injective function, right? So let's suppose that we have a injective holomorphic function, and let's take some disk again. We want the the entire disk, including the boundary, to be in U, right? And let's look at all the W that are in the image of this disk, right? Then for those W, we actually have a formula for f inverse of W, right? It has this integral formula. We integrate this this expression over here over the boundary of that disk, right? Well, that's actually kind of amazing, right? I'm just using the values of the function in an integral formula, and the derivative, and I get the formula for the inverse, right? So let's prove that. So fix a W in here, right? And take zeta to be the zeta that f takes to W, right? So really we want to show that this formula gives you zeta, right? Because that's what f inverse of W should be, right? Now, f prime is never zero. We just proved that. It's an injective function, so f prime is never zero. So that means that this function, as a function of z, f of z minus w, has a simple zero at zeta, right? Because, well, we know that that f of zeta is w, right? So it has a zero, and because the derivative is never zero, it is a simple zero, right? Now, by the residue theorem, so let's just plug this in. I mean, we have the residue theorem for computing these sort of integrals, right? So we plug this in, and that just says that it's the residue of this guy at at zeta, right? Now, because that's this is the that's the pole, right, of this expression, right? And it's a simple pole, right? Because this guy has a simple zero there, right? So if it's a simple pole, it's very easy to compute, right? I just take the numerator, it's a nice holomorphic function, I plug in zeta. I take the derivative of the denominator, I plug in zeta, right? Well, that's just this guy, right? Well, the f prime of zeta, well, that's just some non-zero number, right? Never got into trouble by dividing zero or anything. I can just cancel that. I get zeta. Well, that's f inverse of w. So, right. So I'm done. Now, this has an interesting consequence, which might not be necessarily a completely new consequence, but it's a cool consequence anyway, because you don't have to apply the inverse function theorem now to show that the inverse is holomorphic, right? Because the inverse, near some point, right? So if you look at the image of a disk, that's a disk by the open mapping theorem, right? So and you look at some point over there in that disk, you have a nice formula for it like this, right? Well, it's an integral of something that's holomorphic in W, right? And so we have, so we proved before that, well, that means that this thing is a function that's holomorphic in W, right? So F inverse is holomorphic in W in this entire, it's a holomorphic function of W in this image of this disk, right? So that means that, of course, since I can do it at every point, that it's F inverse is just holomorphic, right? So we don't need to apply the inverse function theorem. We could, right? So the inverse function theorem. Once I know that the that the inverse if the function is injective, therefore its derivative is non-zero, then I know that the inverse function theorem just tells me that the inverse is holomorphic, and I actually have a formula for the derivative, right? So I have two ways of now seeing that the inverse of an injective holomorphic function is holomorphic, right? Now let's just prove the sort of the main thing that we want to prove in this section, right? It's kind of putting things together, right? If we have an open set and a holomorphic and injective function, then the image is open, F view is open, F prime is never zero, and the inverse is holomorphic. And of course, the inverse is also injective, so you can apply the same thing there, right? So it also has the inverse, the derivative of the inverse also never vanishes, and so on, right? Now, basically we've proved all this, right? But we're just putting stuff together. So first, we proved open mapping theorem. That was last time. So we have that F view is open, right? So this all makes perfect. We are actually looking at some open, functions defined on some open set, right? And by the first lemma that we proved, F prime is never zero on U, right? So we've done this, and by the other lemma or by the inverse function theorem, F inverse is holomorphic, right? So so there we go, right? Now, maybe when we talked about the open mapping theorem, right? We said basically the open mapping theorem. One of the things it says is that the inverse of holomorphic functions is always continuous, right? So, as I mentioned, well, better than continuous. It's actually always holomorphic, right? And we do use the open mapping theorem so that we have an open set on which to define a holomorphic function, right? Anyway, so next time what we're gonna look at, we're gonna go to the next chapter. So we're sort of leading up to like one of the big fundamental results in complex analysis, which is the Riemann mapping theorem, basically saying that the only simply connected domains are really the entire complex plane or a disk. So it's up to biholomorphism, so invertible mappings again, right? Now that requires quite a bit of machinery. So the whole chapter is about that, and it also includes another really cool term, which is Montel's theorem, right? So we're gonna next time we're gonna look at Arzelà-Scully, which is really a sort of a real result. And then we're going to build up, to Montel and Riemann mapping. All right, so that's next time. So see you then.